In sediments below Antarctica ice, scientists have discovered a giant groundwater system. This is by Columbia University on phys.org. Today's article: many scientists say that liquid water is a key to understanding the behavior of the frozen form found in glaciers. Meltwater is known to lubricate their gravelly bases and hasten their march towards the sea. And in recent years, researchers in Antarctica have discovered hundreds of interconnected liquid lakes and rivers cradled within the ice itself, and they have imaged thick basins of sediment water under the ice, potentially containing the biggest water reservoirs of all. But so far, no one has confirmed the presence of large amounts of liquid water in below ice sediments, nor studied how it might interact with the ice. But now a team has, for the first time, mapped the huge actively circulating groundwater system in deep sediments in West Antarctica. They say such systems, probably common in Antarctica, may have as yet unknown implications for how the frozen continent reacts to, or possibly even contributes to, climate change. The research appears today in the journal Science. People have hypothesized that there could be deep groundwater in these sediments, but up to now, no one has done any detailed imaging. This is what the study lead author Chloe Gustafson said, who did the research as a graduate student at Columbia University's Lamont Doherty Earth Observatory. She said the amount of groundwater we found was so significant, it likely influences ice stream processes. And now we have to find out more and figure out how to incorporate that into models. Scientists have for decades flown radars and other instruments over the Antarctic's ice sheet to image the subsurface features. Among many other things, these missions have revealed sedimentary basins sandwiched between ice and bedrock. But airborne geophysics can generally reveal only the rough outlines of such features and not the water content or other characteristics. In one exception, 2019 study of Antarctica's McMurdo dry valleys used helicopter-borne instruments to document a few hundred meters of subglacial groundwater below about 350 meters of ice, about 1,000 feet down. But most of Antarctica's known sedimentary basins are much deeper, and most of its ice is much thicker, beyond the reach of airborne instruments. In a few places, researchers have drilled through the ice into sediments, but have penetrated only the first few meters. So the models of ice sheets behavior include only hydrologic systems within or just below the ice. This is a big deficiency. Most of Antarctica's expansive sedimentary basins lie below current sea level, wedged between bedrock-bound land ice and floating marine ice shelves that fringe the continent. They're thought to have formed on sea bottoms during warm periods when sea levels were higher. If the ice shelves were to pull back into a warming climate, ocean waters could reinvade the sediments, and the glaciers behind them could rush forward and raise sea levels worldwide. The researchers in this new study concentrated on a 60-mile wide Willands ice stream, one of the half-dozen fast-moving streams feeding the Ross Ice Shelf. That's the world's largest, at about the size of Canada's Yukon Territory. You can imagine how huge that is. Prior research has revealed a subglacial lake within the ice and a sedimentary basin stretching beneath it. Shallow drilling into the first foot or so of sediments has brought up liquid water and a thriving community of microbes. But what lies further down has been a mystery. In late 2018, a U.S. Air Force LC-130 skyplane dropped Gustafson along with Lamont Doherty geophysicist Kerry Key, Colorado School of Mines geophysicist Matthew Siegfried, and mountaineer Megan Seifert on the Willands. Their mission was to better map the sediments and their properties using geophysical instruments placed directly on the surface. Far from any help if something went wrong, it would take them 6 exhausting weeks of travel, digging in the snow, planting instruments, and countless other chores. The team used a technique called magnetotelluric imaging, which measures the penetration into the Earth of natural electromagnetic energy generated high in the planet's atmosphere. Ice, sediments, fresh water, salty water, and bedrock all conduct electromagnetic energy to different degrees. And by measuring the differences, researchers can create MRI-like maps of the different elements. The team planted their instruments in snow pits for a day or so at a time, then dug them out and relocated them, eventually taking readings at some 4 dozen locations. They also reanalyzed natural seismic waves emanating from the Earth that had been collected by another team to help distinguish bedrock, sediment, and ice. Their analysis showed that, depending on location, the sediments extend below the base of the ice from a half kilometer to nearly 2 kilometers before hitting bedrock. And they confirmed that the sediments are loaded with liquid water all the way down. The researchers estimate that if all of it were extracted, it would form a water column about 220 to 820 meters high, at least 10 times more than the shallow hydrologic systems within at the base of the ice, maybe much more even than that. Salty water conducts energy better than fresh water, so they were also able to show that the groundwater becomes more saline with depth. Key says that this makes sense because the sediments are believed to have been formed in a marine environment long ago. Ocean waters probably last reached what is now the area covered by the Willands during a warm period some 5,000 to 700 years ago, saturating the sediments with salt water. And when the ice re-advanced, fresh meltwater produced by pressure from above and friction on the ice base was evidently forced into the upper sediments. It probably continues to filter down and mix in today, Key explains. The researchers say this slow draining of fresh water in the sediments could prevent water from building up at the base of the ice, and it could act as a brake on the ice's forward motion. Measurements by other scientists at the ice stream's grounding line, the point where the land-bound ice streams meet the floating ice shelves, show that the water there is somewhat less salty than normal seawater. This suggests that fresh water is flowing through the sediments to the ocean, making room for more meltwater to enter and keeping the system stable. But the researchers say if the ice surface were to thin, a distinct possibility as climate warms, the direction of water flow could be reversed. Overlying pressures would decrease and deeper groundwater could begin welling up towards the ice base. This could further lubricate the base of the ice and increase its forward motion. The Willands already moves ice seaward about a meter a day. That's pretty fast. That's 3 feet a day. It's very rapid for glacial ice to be moving. Furthermore, if deep groundwater flows upward, it could carry up geothermal heat. But if that will happen and to what extent, it's not clear. Ultimately, we don't have great constraints on the permeability of the sediments or how fast the water will flow, said Gustafsson. Would it make a big difference that would generate a runaway reaction, or is groundwater a more minor player in the grand scheme of ice flow? To know presence of microbes in the shallow sediment adds another wrinkle, says the researchers. This basin and others are likely inhabited further down, and if groundwater begins moving upwards, it would bring up the dissolved carbon used by these organisms. Lateral groundwater flow would then send some of this carbon to the ocean, and this would possibly turn Antarctica into a so far unconsidered source of carbon in a world already swimming in carbon. But again, the question is whether this would produce some significant effect, said Gustafsson. This new study is just a start to addressing these questions. The confirmation of the existence of deep groundwater dynamics has transformed our understanding of ice stream behavior and will force modification of subglacial water models. The authors are Helen Flicker of Scripps Institute of Oceanography, J. Paul Winterby, Central Washington University, Ryan Venturelli, Tulane University, Alexander Michaud of Bigelow Laboratory for Ocean Sciences, Chloe Gustafsson, now postdoctoral researcher at Scripps. And this is on phys.org. Please leave your comments and thank you for your support. Kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.